Have you ever slipped on a pair of noise-canceling headphones, flipped a switch, and felt the rest of the world just fade away? It almost feels like magic, like someone pressed the mute button on reality. But the story of how we actually reduce sound didn't start in a modern lab. It started in 1978 on a noisy airplane flying from Zurich, Switzerland, to Boston, USA. Dr. Amar Bose was on that flight, excited to try the airline's newly introduced electronic headphones. But there was a problem, one that almost everyone who's flown on a commercial airplane has experienced: constant engine noise. At cruising altitude, airplane cabins typically reach 80 to 85 decibels, about as loud as standing beside heavy city traffic. The engine roar overwhelmed the music completely. Frustrated, Bose pulled out a small piece of paper and began sketching equations. By the time the plane landed, he had outlined a new idea, one that would take years of engineering to turn into working technology. Welcome to Simple Things Surprising Histories. Today, we're exploring the invisible battle happening just millimeters from your eardrums. To understand how we can reduce a sound, we first have to understand what a sound actually is. Imagine dropping a pebble into a calm pond. You see ripples spreading outward in circles. Sound behaves in a similar way, but instead of water ripples, it travels as tiny, repeating changes in air pressure, moving through the air at roughly 343 meters per second at room temperature. When an airplane engine roars or a bus rumbles by, it pushes and pulls on the surrounding air, creating a moving pressure wave. These waves contain regions of higher pressure, called compressions, and lower pressure, called rarefactions, often drawn visually as peaks and valleys on diagrams. When these invisible pressure changes reach your eardrum, they make it vibrate by incredibly small distances, often less than the width of a hydrogen atom. Your brain translates those vibrations into what you recognize as sound. Normally, if you want to reduce sound, you build a barrier. You use dense foam, sealed ear cups, or thick earmuffs to physically block sound waves from reaching your ears. This method is called passive noise reduction, and it works especially well for higher frequency sounds. But on that flight in 1978, Bose wanted to go a step further. He didn't just want to block sound, he wanted to cancel it. This brings us to a fascinating principle of physics called destructive interference. It sounds complicated, but the idea is beautifully simple. Think about basic math. If you have +1 and add -1, the result is 0. Sound waves behave in a similar way. If one sound wave pushes air forward and a second sound wave pushes air backward by nearly the same amount at the same moment, their pressure changes combine. Instead of getting louder, the vibrations shrink dramatically. In controlled conditions, this technique can reduce sound levels by 20 to 40 decibels, enough to turn a loud engine hum into a much quieter background sound. This doesn't mean sound waves destroy each other or disappear completely. Instead, their pressure changes balance out, leaving far less vibration for your ear to detect. You are literally fighting sound with more sound. So how do your headphones pull off this lightning-fast trick? Inside most modern active noise-canceling headphones are multiple tiny microphones, typically one placed on the outside of the ear cup and another inside near your ear. These microphones constantly listen to the surrounding sound, especially steady low-frequency noises like engine hum. When external noise reaches the microphone, the headphone's internal processor analyzes the shape of that sound wave. In roughly 100 to 300 microseconds, less than 1/1000th of a second, the processor generates a second sound wave that is nearly the exact opposite of the incoming noise. This opposite signal, called anti-noise, is played through the headphone speakers. When the original noise and the anti-noise meet near your ear, the pressure changes combine, reducing how much your eardrum actually vibrates. This is why noise-canceling headphones are most effective against steady, low-frequency sounds, typically below about 1,000 Hz, such as airplane engines, train wheels, or air conditioning systems. Sudden sounds, like a dog barking, hands clapping, or a glass dropping, change too quickly for the system to perfectly predict, so some of that sound still gets through. What began as a rough sketch during a frustrating flight required nearly a decade of research and tens of millions of dollars before the first reliable aviation noise-canceling systems appeared in the late 1980s. Early versions of this technology were used by pilots flying the Rutan Voyager, the first aircraft to fly around the world non-stop without refueling. Inside the Voyager's cockpit, noise levels reached roughly 85 to 95 decibels, loud enough to cause hearing damage during long exposure, so reducing engine noise was essential for protecting the pilot's hearing. So the next time you flip that switch and the world grows quieter, remember, you aren't just wearing earplugs, you're wearing a tiny, lightning-fast computer that listens to incoming noise, calculates an opposite signal in microseconds, and uses precise mathematics to reduce the chaos around you. Not magic, not silence from nowhere, but physics working thousands of times per second. Thanks for watching Simple Things, Surprising Histories. If you enjoyed this invisible journey into sound, share this video with someone curious and subscribe for more fascinating stories hiding in everyday technology. Until next time, stay curious.